so we've talked about normal strain. Now let's talk about shear strain, right? So when something undergoes a shear stress, you will often see a shear strain. Strain. Let's pretend I spelled that right. A shear strain associated with, right? So we can think of, for example, a book. So let's take this is our textbook here, right? Ooh, nice textbook. This is our textbook. If I apply a shear strain to this, right? I apply a shear force to this. I can see a shear strain happening where my book deforms and it changes the angle of the pages here, right? So initially it's sitting straight up like this, and then I have this strain that it goes to, and it turns into this kind of parallelogram. So this is the kind of deformation that you see with shear strain. It's a change in the angle, right? So if I were to draw this kind of in maybe a little bit better picture here, right? So we have some rectangle here, and it's sitting at a perfect 90-degree angle, right? So in here, perfect 90 degrees, which is pi over 2 in radians. Perfect 90-degree angle up in here. And then it gets deformed, right? So it undergoes some shear force, some shear, shear like this. See, some shear. And we notice that the angle changes, right? So now instead of that perfect right angle, I have this acute angle. It's not quite that steep. It's a little more like that. Matches this angle here. This angle here is an acute angle. Or it could deform the other way too, you know. If your shear is in the opposite direction, there's your shear. Now instead I have this obtuse angle. Right, here's my theta. So shear strain causes a change in shape from the change in angle of those line segments. So the way we write out our shear strain is with the Greek letter gamma. So this is shear strain, Greek letter gamma. It represents the angle that the change is occurring, right? So like our normal strain was a length per length, this is going to be an angle. And our equation is gamma equals pi over 2 minus theta. So theta is whatever that new angle is. The new orientation angle caused by the shear strain. Pi over 2 is what we assume the original positioning was, right? It was a perfect 90-degree angle, and then we subtract out. So this is our shear strain equation. And an important note on units on this one is that it's always radians. Always, always, always radians, never degrees, because otherwise you're going to mess up with this pi over 2 thing, right? Pi over 2 is radians. Keep it in radians. It gives you an answer in radians. Let's take a look at a quick example. In this example, we have a rectangular plate that's deformed into the shape of a parallelogram. So it's going from this blue shape to this orange dash outline that we have here. And it asks us to find the average shear strain at corner A with respect to the X and Y axes. So what it's telling us there is that our original shape, looking specifically at corner A there, the original shape, pretend that's a right angle. Pretend that looks a little better, right? This original shape here is pi over 2. That's what we're looking at in that corner. But this parallelogram causes this deformation, right? So now we have this new angle theta. And if we kind of overlap these as they're drawn here, to find this angle theta, we're going to have to find a couple of other angles first, right? So we can find this little angle here and this little angle here and use the knowledge that this is pi over 2 to find out what theta is so that we can use our shear strain equation. Gamma equals pi over 2 minus theta. So we have to find what that theta angle is. So we're going to use our small strain analysis shortcut, where we're going to say, all right, for my small strain analysis, if I want to get this angle here, I can use S equals theta R, where now, again, theta is just the general angle. So I'm going to call this, beta, and I'm going to call this angle up here, call this angle is alpha, right? And I want to find this angle theta. So I need to find alpha and beta in order to find theta. So if I use my small angle analysis theory, S is this distance here, and R is the radius that was originally there. So R is that 300. Our theta angle here, this is actually beta for this application, and then the distance that it goes through, here this S is 4 millimeters. So to find angle beta using this small angle theory, beta is going to be 4 over 300. 4 over 300, which when I punch that into a calculator is 0.0133 radians. And I can do the exact same thing to find alpha. Right here, my distance S is the angle, alpha, R, where again, that distance R is that arm reaching out, so that's the 400. And then the S is that little change in distance, the 2 millimeters. So alpha is 2 over 400, or 0.005 radians. All right, that's easy enough. And now I can just kind of plug everything together, right? So my theta is going to be this pi over 2, right? If I kind of construct what the equation is for theta, theta is going to be pi over 2 plus the beta term minus the alpha term, right? Does that make sense? The only way we can find theta is we know pi over 2 plus beta, right? We can add those two together and that gives us the full arc length here. And then if we subtract out alpha, then we'll just be left with theta. So theta is pi over 2 minus alpha plus beta. Right, so subtracting out that portion, adding the beta portion, that gives us theta. And we can plug this guy up into our shear strain equation. I'm going to actually bring that down here. Gamma is pi over 2 minus theta. So gamma is pi over 2 minus pi over 2 minus alpha plus beta. And I can go ahead and simplify that out, right? Makes it really nice because my pi over 2's cancel out now. So gamma, my shear strain, is going to be, alpha, sorry, not beta, alpha minus beta. Distributing that negative sign, I get alpha minus beta. So that is 0.005 minus that other number, 0.0133. And that gives me negative 0.00833 radians. Shear strain can be positive or negative. It depends on whether your angle is acute, whether theta is an acute angle or an obtuse angle. Right, so if you have this this wide angle, this obtuse angle, this would be a negative shear strain, and an acute one would be a positive shear strain. So it can be positive or negative. Just leave whatever the sign is that you get on there. This one came out to be negative. So this is our shear strain. Again, keep in mind that small angle theory, it can be a little, different, a little uncomfortable maybe to be taking such a shortcut, but it can save you a lot of time in the trig again. Again, we would have had to do a lot of trigonometry here to get this to work out, but instead using that small angle theory, we were able to get our shear strain relatively quickly.